I believe the next speaker is in the room as well. So next talk is on functional causal Bayesian optimization. Is this a in person? Yeah, thank you so much. Beautiful. So please try to stick to your 20-minute time.
Okay, I shall try. Hi, everyone. I'm Limor. I'm here to present this work on functional causal Bayesian optimization, which I completed during my time at DeepMind with Virginia Aglietti, Alexis, Bellot, and Silvia Chiappa. So briefly, a quick overview. What we're trying to achieve here is an extension of causal Bayesian optimization, CBO. Some of you may be familiar, others, don't worry, we'll catch you and bring you up to speed. The letter CBO considers hard interventions as the main tools to find an optimal treatment. And in functional causal Bayesian optimization, we're essentially asking, why stop there? We may in fact find more optimal interventions and additional benefits by considering soft interventions as well. And why is that? Because we're actually going to show with some results that hard interventions can be suboptimal in certain settings. And we will demonstrate why and suggest an alternative method, including some examples to demonstrate how we can, in fact, reap the benefits. So CBO, just as a quick overview, is going to mainly operate with hard interventions to find some kind of optimal target effect in the system. We have a specific target variable in mind. In this example graph, it's going to be PSA. And with a hard intervention, we can set the value of some subset of our intervenable nodes in the graph to certain values, little x, this could be a vector of scalars. And we're going to be, with our hard interventions, replacing some causal mechanism that was in place in the observed system with a direct delta distribution that's going to be centered at specific values, little x. So for example, in this graph, we replaced the previous mechanism that determined the value of statin with direct delta centered at 0.7. And by that, we replaced a mechanism that had a dependency on age and BMI with one that is essentially agnostic to them. The goal overall is to find the optimal subset of intervenable nodes to intervene on and the values to set them to. And that in order to minimize a certain causal effect on our target variable, which will in this case be the expectation of PSA, given the intervention do of x equals little x. So the formal problem statement will look like the following. We're looking for an optimal intervention set and associated values. We're going to be argumenting over a space that's made out of the power set of intervenable variables and domain of possible allowable values for each. And we're going to be optimizing the target effect, in this case, minimizing the expectation of y given do x. With the running example that we have a target variable, as we said, PSA. The intervenable variables are all the ones appearing in gray, and the power set will be the search space over them. And what we find in this particular setting is that the optimal intervention will be on CI, statin, and aspirin, and we're going to be setting them to the values 1, 1, and 0, for example. However, there is a whole other world of interventions out there, soft interventions, which we can refer to them generally as everything contrasting with these kind of static value assignments that we do with hard interventions. We can, in fact, replace the causal mechanism that was in place with another conditional distribution, pi of x given cx. Those CXs will be new parents that we're associating with our intervention nodes. We're going to be calling them contexts. So in the graph that we see to the right, this is the observational graph G. And we can envision an intervention on statin that will take age and BMI as contexts. And that could look like replacing the original mechanism P of statin given age and BMI with a new pi that still depends on the same values, potentially has a different relationship or mechanism associated. So what we're going to achieve by extending our view and looking to fCBO is a way to find targeted and more personalized treatments in this system. We can achieve subgroup optimality, meaning that instead of focusing on a single target effect for all possible context values, we can now take context into account and make sure that we're not just optimal in some average sense over the population, but actually find target effects that are optimal for subpopulations thereof. And we can also find lower cost treatments that would focus on most needed or most promising parts of the context, depending on how we define the problem. And hard interventions are in fact just special cases of soft ones. So we're in fact not losing everything. If a hard intervention is the optimal thing to do, we will still recover it. So from CBO to fCBO, we will need to change our problem formulation a little bit. We will now be looking for optimal mixed policy scopes, MPSs, and realizations thereof. And we're going to be arguing over a different space that's made up of the set of all MPSs and their possible realizations. And the target effect is, of course, going to be not with respect to a hard intervention, a do intervention, but the soft realization that we're picking. So you see this term MPS come up a lot. Let's define it. A mixed policy scope S is just a collection of tuples, X and CX, where X are the intervention nodes, which will be some subset of our nodes I. Well, in fact, in each tuple, it will be a single intervention node that's a member of I. And CXs will be the associated set of context with that X. And the only thing we need to watch out for is that by defining these MPSs, we're not introducing any cycles into the graph. And that's because each CX is going to have edges pointing into X now. So we just need to be careful we're not introducing cycles. This is borrowed from Lee and Barenboim 2020, which already defined these MPSs, including the reduced search space that one would need to consider, such that we don't repeat ourselves with redundant interventions. So with a running example, what would an MPS and realization look like? So we now have a certain collection of tuples that would capture an intervention on statin and aspirin with age and BMI as the context for both, as well as a hard intervention on CI, which notice will just be represented with the empty set as the context for CI. So this is again to demonstrate the point that we're not losing anything. We're still as expressive and more expressive, in fact. And the realization of pi s will be pi's, let's say, of the following form. So pi of statin given age and BMI could be a delta function that's centered at a linear combination of age and BMI. And the pi of CI will just be, again, reduced to a hard intervention. That's the familiar do. Of course, pi can also be a stochastic intervention. For example, a distribution that's mean is centered at a linear combination of age and BMI. But in this work, we're going to focus on deterministic soft interventions because it was already shown that those would be optimal for the purpose of finding an optimal target effect. So the contributions and challenges we faced in this work, first of all, were from a conceptual theoretical standpoint. We wanted to show more formally why we should care about soft interventions. Of course, intuitively, we already explored why we may care, but we wanted to show how and when. So I'm not going to go into the full details here, but we showed when suboptimality of hard interventions may arise under two conditions. One of them is in the case where we have a non-intervenable node, such as W in the graph above. It has a path to the target we care about, Y, and we can use it according to a valid MPS when we determine the value of X. So in fact, we're going to argue that in such a case, one definitely should consider soft interventions because this edge from W and Y holds certain information that we can use by using W as a context to X when we determine its value. The second condition will arise in, it's a similar logic, but would arise in the case where we have unobserved confounders. We also show formally why our new Parham formulation in equation 1 can recover an optimal target effect for different groups in the population. So this is the subgroup optimality idea. And we show that when we perform hard interventions, we may in fact sacrifice parts of the context space in order to optimize an overall target effect that's an average over the whole population, but that could be at a disadvantage to certain groups, let's say if we think of them in terms of different age groups or different genders and so forth in a population. And with the approach of taking soft interventions that are contextual, we can use this to find treatments that are optimal for the whole context space. From a technical standpoint, we needed a new methodology that will allow us to deal with functional GP models, because now we are the inputs to our GP that will model the target effects will need to be functions. So we needed to think carefully how to do that and how to construct a kernel that can measure distances between soft interventions, meaning functions, but potentially also a mix of soft and hard interventions. So I'll give you a glance at it. At CBO, we had 3 main points to the methodology: how we reduce the search space to make sure that we use the causal information that we have to not look over an overly big search space than we actually need to, so we can already remove some redundant interventions that we don't need to visit. From a GP model surrogate perspective, we now model each MPS target effect, and we're going to be using a functional Gaussian process to model those, and we'll be computing distances across MPS interventions, which will require a specialized kernel construction. And also the acquisition function will now need to be an acquisition function now. So again, as a broad overview, we will have these surrogate models that model these different mu of y under different MPS interventions S. And we will have a prior mean function L initialized at 0. And most importantly, we will have this kernel now that will measure distances across functions. This is going to be a prior covariance function L, which is an RBF kernel with certain hyperparameters. And these different surrogate models will now be mappings of a functional objective from the space of pi s of all bounded vector valued functions on the union of the contexts that make up each MPS S. And that will be a mapping from those functions to the reals. Okay, so once we've constructed the GP, the details are in the paper, unfortunately, due to time. The algorithm will follow pretty closely to what you may be familiar with from CBO or other Bayesian optimization settings. So the first step we're going to take is reduce the search space with our causal information in order to find this mu sigma that we actually need to consider. And then at each trial, we're going to be maxing an acquisition function L. We're going to be obtaining the associated target effect, update our interventional data set, and perform a posterior update. Again, the devil's in the details of how we actually construct this covariance or the kernel, but yeah, you're going to see more in the paper. So third, let's just take a couple of example experiments that we ran. One of them is designed to demonstrate the subgroup optimality takeaway, and the other one in the healthcare setting that we've been using as an example all along will showcase the idea of cost implications of these functional interventions. So the first idea, the subgroup optimality, can be seen in this augmented chain setting. Overall, I hope you can see the edges. I see they're quite faint here, but we have X pointing into Z and into Y. We have Z pointing into Y and W into Y as well. And the key takeaway here is actually in the structural equations. So you see that the equation for Y includes an interaction term between Z and X. That actually tells us that depending on the level of X, which is a non-intervenable node, we may want to assign a different level to Z. In particular, if X is negative, we would want Z to be negative as well if we're trying to minimize Y or the expectation of Y, and vice versa. So this interaction term is one example in which actually taking X as context when we are determining the value of Z will allow us to find more optimal interventions rather than a hard intervention that will just pick one value that may disadvantage one group or another. So to demonstrate that, what happens in the experiment itself is that indeed fCBO can uncover a more optimal intervention that will find a lower target effect compared to CBO and some other existing alternatives. But the key takeaway on the right is we're demonstrating it through an object we define, P gain, that will take in both the intervention we found, pi of S, and the subgroup that's going to be defined by this C, different values of C. In this case, it will be, we're defining it as whether X is negative or positive. And what you find in these bar charts to the right is that fCBO can in fact find an optimal intervention that will treat groups similarly in terms of the gain that's going to be achieved in terms of the target effect under the intervention compared to the observational setting. While CBO, as we know, will have to pick one group over the other. In this case, it's going to prefer the negative X group. Okay, and in the healthcare example, just to give you a flavor of what the search spaces would look like after reduction. So we have MG for CBO and M sigma for fCBO. First, we can already demonstrate that we can find a more optimal intervention with fCBO. But the interesting part is the cost implications. So we can define cost in this case as the area under the graph of our intervention over the space of contexts. That could capture an idea of units of allocation. So we can define the cost in terms of how many intervention units have we given. And as you can see, the one that will be found by fCBO will be very picked and targeted at specific areas of the context space, while CBO will have to pick something quite uniform that will have to give the same intervention value to everyone in the population. And that means that fCBO can actually be much more targeted with its units of allocation, which is in fact what happens here. And you can see that the cost in terms of area under the graph is indeed lower for the more optimal intervention found by fCBO compared to what CBO can do. So this is the broad overview. I hope that I kept to my time. And the takeaways, as we mentioned before, are these ideas of targeted interventions, subgroup optimality, lower cost associated, and in fact, that we're not losing anything in terms of recovering the optimal intervention. That's it. Thank you.
Thank you for the excellent talk. So our discussion is going to be Rohit Bhattacharya, and he's also in the room. Perfect. So.
Yeah, thank you for a really clear and beautiful presentation, Limor. So yeah, the paper, as is required, is kind of technical, but it's beautifully presented. So congratulations to the authors. Highly recommend reading it. The authors walk you through with some nice examples, all of the technical details. I think this is really important work because soft interventions relative to hard interventions is kind of understudied by our community. And if you think about it, having a uniform prescription of some intervention to everyone in your population is kind of unlikely in many real world settings. So if you prescribe an exercise regime of run 10 miles, do 100 push-ups, 100 squats, 100 pull-ups, that might kill some people in your population. You want to, have some prescription based off of current physical ability. I mean, that would certainly kill me. The fact that this paper really seriously considers soft interventions is amazing. So just two conceptual questions I had, and maybe it leads into some nice future work, is so we're kind of in the home of causal discovery. So my first question is, one of the inputs to this algorithm is a specified causal graph. How robust can we make some of the propositions? So like proposition 3.2 about the optimality of hard versus soft interventions. how robust can these algorithms be made to a misspecified causal graph or one that you learn from a causal discovery algorithm? So maybe you know up to Markov equivalence. And then question 2 is, can we be more formal or elaborate a little bit more about the qualitative and formal semantics of a partially causal model? So in some of these, in this graph, some of these nodes are considered non-manipulable, so the green ones. And if you look at them, you know, things like BMI, we know pretty well that BMI is an ill-defined variable in some ways, and interventions in BMI are ill-defined. So how do we more concretely think about these non-manipulable variables? Maybe looking to some of the epidemiology literature on that. Yeah, thank you.
Thank you so much for the great questions. For the first one, I would say this is not something we looked at, of course, as future work. I think it's a very important question. Within the CBO world, there was already work that looked at what do we do when we don't start with a fully known graph. And I think one of the key advantages of this overall framework is that we do have an interventional budget, if you like, and we can collect interventions. So we're not sort of forced to rely on what we have just from the observational setting. So I definitely think there is a way to combine some of the pre-existing work on actually recovering the graph as we go through the trials, and not just rely on full knowledge of the graph, which I agree with you for many real world settings would make a big difference. So that's one. For the second one, it's a great question that we keep coming back to throughout the causal literature, right? And the usual answer would be, well, domain knowledge. How true that is to all use cases, I'm not sure. In this particular graph that you looked at in terms of BMI and height, this is actually taken from a pre-existing work from the healthcare literature. So in this case, we just could, in fact, rely on a graph that was given to us and make some pretty concrete assumptions about it. And yes, I think that in, let's say, healthcare domains and as well as other sort of safety critical settings, we would definitely look to the experts first to ask them what they would do and what they would allow in terms of intervenable versus not. But whether there are other cases that are a bit murkier and where we may want to actually take that into account into our method and, you know, give some experimental budget to some nodes that could be intervenable and see whether it makes sense to allow interventions on those, yeah, is also something that's definitely worth looking into. Thank you for the great ideas.
We have time for a quick question. Any questions? Yes.
Can you comment on the computational complexity of the algorithm that are involved in this optimization task?
Yeah, so I believe we did include it in the paper, and it is cubic, if I remember correctly. Sorry, in the number of variables, as far as I remember.
So it's puzzling because normally optimization, any optimization task in a traditional setting in graphical models, selecting subset of variables that optimize something is hard. So you assume probably different setup than what I have in mind. So the setup is that you have observational data and the graph only.
Yes,
Okay.
yes, that's right. That's what we start with. We do reduce in terms of if there are redundant interventions in terms of the relationship between context variables, interventions, and target. But yeah, we can discuss this.
Yes,
offline.
okay, thank you.
Thanks.